event, and I want to introduce our work for the distributed quantum computing based on Cisco quantum network. Then today the talk will be in three different parts. First, we will talk. I want to address the Cisco vision on applications for quantum networks. This not only includes the quantum data center or quantum computing, but also include for other applications we are interested in. The second part, we will talk about our framework, like we want to how do we execute a quantum circuit in a quantum network using the distributed quantum computing. And then the third part, we would address each individual technology we are developing to achieve this goal. So as Matthew has mentioned, quantum computing is a very powerful technology that can solve many complicated and challenging tasks in real life. But in order to make these applications work, usually it requires multiple millions of logic qubits, which is very challenging. Even though on the serious side, people are trying to lower the requirement of this number of qubits, but it is still much beyond the limitation of a monolithic quantum computer. Therefore, people now consider using a quantum network to interface multiple quantum computers, monolithic quantum computers, to build distributed quantum computing can be a powerful solution to achieve real advantage for the many tasks we are interested in. So at Cisco, our main goal is trying to develop a quantum network for distributed quantum computing, and we call it quantum data center. This is the first task we focus on. And second, in the meantime, we are also interested in using quantum networks for classical applications. And also we have some works also on the quantum safe communications like QKD and related stuff, but that's not our major focus right now. So here's a summary of all the applications we are working on at the moment. The top four are the classical applications using the quantum network. The first one is the decision coordination. We can use the entanglement distribution to make instantaneous decision coordination between multiple parties. And this decision making can benefit some financial benefit in the financial industry. For example, paper had discussed using this decision coordination for high frequency trading, and we can have some quantum advantage in the winning rate. And then for the secure position verification, people can use distributed entanglement for better authentication of the location of the users. People can use this in the military applications and also finance applications. For the time synchronization, the one we are discussing here is mainly using the quantum technology to enhance the classical time synchronization. So it is not considering quantum true quantum advantage in this application. We are still limited by the standard quantum limit. The last application we are interested in is use quantum safe network. One good example is QKD, but besides QKD, we are also looking at using quantum signals for eavesdropping detections. Besides these four classical applications, we are mainly working on two major distributed quantum information applications. First one is a ultra precise quantum sensing. This is distributed quantum sensing is mainly aiming at going beyond the classical limit, so that we want to reach the Heisenberg limit. This includes the distributed quantum phase estimation, which can be used for the biomedical imaging and other sensing applications. And also this is our, the last one is quantum data center. This is our main focus. We are developing a quantum network framework for the distributed quantum computing. And this is also the main topic of today's presentation. So this is a timeline that we are advertising the public. The first timeline is borrowing from the major computing vendors, including IBM and Google. And according to their timeline, we are putting our timeline downstairs. And right now, we just started our development on quantum networks, including both hardware and software. And in the meantime, we are also working on applications for the classical application, as I mentioned before. These are also ongoing projects we are working on. And we are aiming to provide a demonstration of concepts, full stack, single rack quantum network solution for distributed quantum computing at 2030, and we are aiming to scale it up for the data center application in 2035. Okay, so that's all the background. So let's move to the distributed quantum computing. Um, for quantum data centers, Cisco's vision is trying to develop a universal quantum network solution, which provides a full stack solution for executing remote gates and circuits. In this case, we are not aiming at one single modality of the quantum computing platforms, but also considering both all possible candidates. And these three candidates are the major candidates we are considering right now, but we are also having the internal investigation of photonic and color center platforms as well. For our quantum data center network, we develop our efforts into two major parts. One is we called quantum network fabric. We call Q fabric. This is mainly for the hardware. And then the second part is called Q orchestra. This is mainly for the software part. So before we move to details, I mean, I'm a hardware background person, so maybe some languages sounds very weird or confusing to you guys. So if you feel like confused, just jump out and ask me to clarify that. Um, in our full stack solution for the quantum network orchestra, our main goal is trying to develop a quantum computing compiler, which includes the network compiler as well. It will be multi-tenant network aware, trying to minimize the network latency and network resources for executing remote circuits. And also, we are developing network protocols. I will show the details of these protocols and softwares for entanglement distribution later. Talking about the hardware layer, we are developing quantum entanglement source, quantum net interface cards, which is mainly the quantum interface like frequency converters, and quantum measurement systems, quantum switches, and quantum memories. And also each individual technology will be introduced later. So by combining both Orchestra and Fabric, we are going to use all the technology we are developing to execute a remote circuits. If we break down the execution of a remote circuit, it can be developed into the following steps. At the very beginning, we can have our user define a quantum circuit into our system, and the Q-Orchestra will check the network and this circuit to determine the best network topology for this execution. After that, based on the available resources and network topology, our compiler will start doing the circuit partition. After the circuit partition, next goal is trying to use our developed dynamic scheduler to minimize the time and the resources required to execute those remote gates and internal gates on each individual quantum processing units. After the Q orchestra, we will start our hardware layer by starting with the synchronization through the entire network. And it includes the synchronization between all the QPUs and switches involved in the execution of this quantum circuit. After that, we will reconfigure the quantum switch based on the synchronization and the circuit partition. Then we distribute the entanglement via our entanglement source between QPUs, or we leverage the QPU itself to emit photons to entangle to do the bell swapping at our switch. At the end, we will communicate the measurement results between QPUs to make sure the entanglement distribution has success, and we can execute each remote gates inside a QPU. And then we want to talk about each individual technology we are developing inside Cisco. At first, I will talk about the two major topologies we are investing right now at Cisco. So for a data center, there are two major type of topology. One is called switch-centric. In this scenario, which is the topology on the left-hand side. This is a class network topology, which is a good example of switch-centric topology. The benefit of using this guy is that all the routing and the interconnection will be from the optical switch. And by doing so, we can have all the QPUs purely doing the computational tasks. Therefore, all the QPU resources will be only for the computational, so that the execution of the circuit efficiency can be maximized. And in the meantime, all these memories will also be hooked up onto our switches. Um, but the problem of this topology is that if we want to scale up the entire data center to a very large scale, we require very high dimensional and fast, low loss and low crosstalk switches, which does not exist at the moment. So we need to develop a new switch technology to make it happen. As a comparison, the second possible topology is called server-centric. This is a On the right hand, this is a B cube topology, which is also a good example of the server-centric solution. In this case, compared to the switch-centric, our QPUs uh, will also provide the routing and interconnection functions. And also in this case, each QPU have to allocate some memory qubits for the memory purpose for the entire network. The good thing for this topology is that it does not rely on the high-dimensional fast and low-loss switches, so that even with the current state-of-the-art switches, it's still possible to build a large-scale network. But it requires a lot of resources from the QPU. Therefore, unless we have a super powerful QPU for each individual node, it's gonna take a lot of resources and lead to a big overall overhead on these computational resources. Um, After determining the topology, we will do our circuit partitioning. So in San Cisco, we are developing a new enhanced window-based circuit partition for better circuit compilation. So the conventional circuit partitioning is aiming to optimize the entanglement distribution inside one QPU. But now in the distributed quantum computing, the circuit partition will be also including the optimization of the entire network as well. The previously developed window-based circuit partitioning is mainly looking at inter-window gate teleportation. However, we find that if we also including the gate packing and the intra-window state teleportation, actually we can have more remote gates inside each window so that the execution of the circuit can be more efficient because of the less entanglement pair distribution is required. After the circuit compilation, we will use our dynamic scheduler to optimize the time of execution of the circuit. So in the single monolithic quantum computer, scheduler is mainly looking at the job allocation between different qubits and trying to minimize the entire time cost and resource cost inside each QPU. However, for our network scheduler, it also has to consider the network resources consumption. And for our case, we develop a dynamic network scheduler because the EPR distribution inside entire network is actually a probabilistic process, and we can leverage the probabilistic process to make the entire scheduling become dynamic. The example we show here is consider a 6 QPU case. In the conventional static scheduler, the execution of the signal gate has to happen for each layer in sequentially. For example, in this case, we have to execute the signal gate between QPU 3 and 4, 1 and 2, and 5, 6 first, and then we go to the 1 and 4 and 2 and 6 later because they have correlations between them. However, when we do the entanglement distribution inside a data center network, because the success of this EPR distribution is probabilistic, we can actually move part of the entanglement we can move part of the signal execution to a earlier time once we have all the pre-request condition matched. Therefore, by doing such a dynamic scheduling, we can save the total amount of time for finish the entire execution of the circuit here. And when we finish the scheduling, we need to move from the orchestra to the quantum fabric. Means that we need to start our hardware layer by starting the synchronization of the entire data center. Um, the data center environment is quite different from the metropolitan area network, which is mainly studied in the past couple years. In the data center, the entire network size is small, but it has more complicated connectivities between different racks and QPUs. The network topology is predefined, and all the delays between racks and QPUs are also predefined. However, because the execution of the circuit requires a dynamic reconfiguration of the network rapidly, using very rapid will not be good enough for the network in synchronization and initialization. Mainly because that the initialization of the very rapid for a single pair of connection takes very long. And the reconfiguration of the network is usually like millisecond level, which is not long enough for very rapid. The current solution from our side is that we pre-store all the possible connections from each rack to each between each racks, and then we use that pre-stored information as a starting point to reduce the amount of time for the reinitialization for the network synchronization between circuit execution. Um, After the synchronization of the entire network, we need to reconfigure the entire switch. One network switch, from Cisco's perspective, we consider the entire network we want to have the entire network to share the quantum resources by developing such a top of rack switch. Means that each rack we have multiple QPUs, but we only have one central switch with all the shared quantum resources. This is mainly because first, quantum resources are very expensive. Having multiple resources distributed on each QPU actually adds a lot of engineering overhead and cost overhead. And the second reason is that the execution of the quantum circuit and the entanglement distribution is actually probabilistic. Therefore, by using a dynamic scheduling and compilation, as we talked before, it is possible to share the resources as the central switch. In our case, we want to hook up all the bias environment, entanglement source, and quantum memory, and quantum interface card onto our reconfigurable optical switch. Also, it is worth mentioning that even this entire switch looks only available for the switch-centric topology, but we also show that this design can also help the server-centric topology as well. So talking about entanglement source, currently we have two entanglement source under development. This is a quantum chip we got from UC Santa Barbara. So we revised their design to have a multiplexed quantum entanglement source so that each quantum chip has multiple rings and it can generate multiple pairs of the entanglement spanning the entire DWDM channels. By using this source, we are aiming to provide continuous entanglement distribution between switches, and then once the entanglement distribution exceeds, we store the entanglement into the quantum memory, so that once the QPU requests the EPR pairs for the remote gate execution, we can call out those EPR pairs directly from the memory without waiting for rebuilding the entire network connections. And the second quantum source we are using right now in the lab is from our collaborator at QNet. This quantum source, the unique part of this quantum source is that it is a non-degenerate source, means that one color of the photon is at a telecom band, which is good for the networking purpose, while the other one is actually at the near, which is 795 nanometer. By using such a non-degenerate quantum source, we can easily interface our local qubits, like cold atom quantum computings using rubidium, to the network without developing a specific quantum frequency converter. Um, After talking about the excuse me, our entanglement source, we will move on to the quantum switch. In order to achieve our demonstration of the quantum data center, we have to develop a new quantum switch, mainly because the current state of the art of the switch cannot satisfy our requirement. We can divide the current switch into two major categories. One is the mechanical switch, which has very high dimensionality, low crosstalk, low loss, but suffers from very long reconfiguration time, so that the speed is very low. And the second category is photonic quantum switch. This kind of switch usually is very fast, but the dimensionality is low because the loss is high, and the crosstalk and loss are also very high. And another problem of the photonic switch is that this photonic devices can only support one type of polarization, which is TE mode. Therefore, for polarization encoding, or the encoding, which is mainly used in cold atoms and trapped ion quantum computers, it is very hard to switch those atoms without losing the quantum entanglement. Therefore, we are developing such a photonic quantum switch by using by converting the polarization entanglement to path entanglement. Our architecture is shown here. At the beginning of the switch, we use a polarization to path converter to convert both polarizations into two different paths. And then we have two matrix switch, which is based on Mach-Zehnder interferometers, to do the switching for each individual photon. And after the switching, we will combine the two polarizations as the polarization to path converter. By doing so, we can have a efficient and effective routing of the polarization entangled photon without losing the entanglement. The current development of the photonic quantum switch is still at a very early stage. But in the meantime, we are considering to leverage to develop a reconfigurable quantum interface to also provide some degree of the routing of the entire network, so that we can use the current mutual mechanical switch to achieve high-speed switching. And also, this reconfigurable quantum interface can also provide a multiplexing of the entanglement photons, so that we can, in principle, we can improve the entire entanglement distribution rate from 100 kHz to 188 MHz. And our simulation rate here at 4.5 MHz is based on the experimental numbers we have in the lab. And all these technologies we discussed is now under the Cisco Quantum Network Development Kit. So this is a software platform that we want to build the quantum simulation, quantum emulation, and connect all these into our real hardware and software within one single toolbox. Our software team is currently working on this application, and we are trying to connecting all the hardware and software we are working on into this platform, so that our users can leverage this platform to use and to do their own simulation or the emulation. So this is my talk, and this is our excellent team at Cisco. Also, we are hiring, so if you are interested, please contact us. Thank you.
One question maybe? Yeah.
No, sorry, no, I was going to ask. I think I have a comment, not a question. I think it's a really impressive scope of work with such a small team.
Oh, thank you.
I wonder, like, maybe this is a question, like how much of the work has already been, hardware, for example, have already been implemented, be there, or how much this is like your vision or plan?
Oh, okay. So let's go back to previous slide. So for the software part, For example, the dynamic scheduler and the circuit partition, we already have the paper published on archive. So right now, our software team, so the team I showed is mainly the research team, but we have a software team, software engineering team is working on implementing those two
Right. So like
onto the QNDK.
the hardware part. How about the hardware part? I think software is.
Okay. The hardware part. So, this photonic chip, the first generation of the chip is already in the lab. We are building the demonstration of the concept network, multiple users through using this chip in our own lab right now. So this one we are also building another network. Mainly want to interfacing this guy with a we want to convert this guy we want to combine this guy with this concept together, and this is the demonstration concept we are working on right now. So we have
So
we
the
have the
switch-
experiment. The switch itself is under fabrication. The design is already done.
Okay. Thank you. Very impressive. Thank you.
Yeah, thank you.
So I think maybe we can just sit around together.
What about, we have a panel, I don't have.
Yeah, we have a short panel. I think mostly we'll be answering questions.
Right, it's just to discuss ourselves.
Exactly, yeah.
Yeah.